You know that feeling when you ask an AI a highly specific question about, say, your company's private data or maybe a breaking news event from just this morning, and it gives you a super generic or worse, a completely hallucinated answer? It is incredibly frustrating, right? Look, large language models are absolutely brilliant, but they have a fundamental limitation. They just don't have access to specific, private, or up-to-date data that wasn't included in their original training set. The source material we're looking at today tackles a really fascinating question. How exactly does an AI learn what it doesn't already know?
Welcome to The Explainer. Today, we are diving into a technology that is completely revolutionizing how AI accesses information. We're talking about Retrieval Augmented Generation, or RAG. We're going to use some brilliant insights from our source material on ChromaDB, MilvasDB, and multimodal RAG to figure out exactly how these advanced systems work step by step. It's a real game changer.
Here is our roadmap for today. We'll start by decoding RAG systems, then we'll break down tokens and embeddings, look at the role of vector databases, build a LangChain pipeline, and finally, explore the incredibly cool world of visual RAG. All right, Section 1, Decoding RAG Systems, the 3 pillars of context.
So let's unroll this pipeline and look at the 3 foundational pillars of context. RAG stands for Retrieval, Augment, and Generation. Step 1 is retrieval. This is where we actually find the relevant external data out of, millions of documents. Step 2 is augment, where we take that raw data and combine it with your prompt. And step 3 is generation, where the AI finally creates the informed answer. But here's the secret. 80% of the engineering magic, it actually happens right there in step 1. If your retrieval is bad, the whole system basically falls apart.
Moving right along to Section 2, Tokens and Embeddings. Going from words to math.
To pull off perfect retrieval, we have to translate our human words into a language the AI actually understands. And that language is math. AI doesn't read letters, right? It reads what we call tokens. For example, an older model like GPT 3.5 might look at the word Pakistan and just break it down into multiple token chunks like PAK and ISAN. But a more mature model like GPT-4, it recognizes Pakistan as a single unified token. And this is a big deal because this dictates exactly how the AI interprets and searches through all your data. And this matters tremendously in the real world. Think about it. If you use a standard general-purpose tokenizer on highly technical data, like patient medical records, it's going to chop complex medical terms into totally wrong pieces. That completely ruins your retrieval accuracy. So in specialized domains, you absolutely must use specialized pre-trained models. A great example is Google's MedPalm 2, which is designed to understand the exact, specific boundaries of medical terminology.
Okay, so once our text is properly tokenized, what's next? We embed it. We turn it into a vector. If you take a question like, what is the meaning of life, and run it through Google Gemini's text embedding model, you get this massive array of numbers back, specifically 768 numbers. Your question gets converted into a highly precise 768-dimensional vector floating in a 3D space. It honestly blew my mind to learn that every single sentence you process through that model will have a length of exactly 768.
Which brings us to Section 3, the role of vector databases, storing the math.
So where do we actually put all this math once we've translated our company's data? Well, that's where vector databases like ChromaDB or Milvas step in. They exist for one primary reason, and that's to calculate cosine similarity. Now, the crucial point here is understanding what that dense math term actually means. Imagine your 768-dimensional vectors as lines pointing in space. Cosine similarity is simply the mathematical angle between two of those vectors, like your search query and a document sitting in your database. The smaller the angle between those two lines, the closer they are in contextual meaning. So phrases like I love my country and Pakistan Zindabad will have a very small angle between them because they share a really strong semantic match.
Back in the early days of machine learning, developers literally had to manually write these complex NumPy functions just to find these angles. It was a lot of work. Today, a database like ChromaDB just automatically handles all the complex encoding, the cosine similarity matching across millions of records, and the decoding back to human text. It does all the heavy lifting for you.
Section 4, Building the LangChain Pipeline. Let's connect the dots. Okay, we've got our embeddings, and we have our vector database. But to glue all these disjointed components together into a system that actually works, LangChain acts as the pipeline. Let's walk chronologically through the micro moments of a single query. Ready? At 0 milliseconds, the vector search retrieves the raw, relevant data from ChromaDB.
By 10 milliseconds, a LangChain component called a runnable lambda temporarily loads and processes this data in memory. At 20 milliseconds, it hits the prompt template to format the context. And finally, by 50 milliseconds, it is handed off to the LLM to generate your final answer. It is incredibly fast and so structured.
And right there at the 20 millisecond mark, tucked inside the prompt template, is the absolute most important guardrail of our entire system. This is where we explicitly command the AI, answer this question using the provided context only. This right here is the secret to stopping the AI from hallucinating. The system strictly confines the AI to only look at the exact documents we retrieve from our database. No guessing allowed.
Just look at the massive difference this makes in practice. If you ask a standard LLM to tell you about cats, it just spits out this rambling, generic encyclopedia entry pulled from random corners of the internet. But a properly built RAG LLM, it provides a highly specific answer based only on the custom documents we actually uploaded. In fact, in the source material, there's a great example where the system was asked about sharks, but it was only provided context about goldfish. Instead of making something up, the system correctly replied that it couldn't answer the question. That is the true power of a controlled RAG pipeline.
Finally, Section 5, Visual RAG, moving way beyond just text.
So, what if we apply this exact same logic, not to text, but to images and audio? Welcome to Visual RAG. Now, just like before, choosing the right embedding model is critical. If you feed a picture of a face into a standard image model, it just broadly categorizes it as a person. It can't tell you who it is. But a specialized model designed by Google researchers called FaceNet works completely differently. FaceNet actively ignores the background, the chairs, the lighting, the whole shebang, and extracts only the exact, unique facial features: the eyes, the nose, the ears.
And just like our text model turned words into 768 numbers earlier, FaceNet converts those unique human facial features into exactly 512 dimensions. So every human face becomes a precise mathematical vector of length 512, totally ready to be stored in a vector database and matched up using cosine similarity.
The real-world applications for this are absolutely staggering. Our source notes a startup that recently raised $7 million using this exact technology to create animal passports. Get this, just like human fingerprints, cows have entirely unique nose print patterns. By embedding these nose prints into vectors, they can literally track livestock with perfect accuracy. You can also use this for security, matching CCTV faces against a massive national database in milliseconds. Or apply it to audio. By using an audio embedding model called YAMNet, you can identify distinct speaker voices in a transcript, automatically tagging exactly when speaker A stops and speaker B starts talking.
We have gone from basic text retrieval to translating the entire physical world, faces, animal prints, human voices, into searchable math. So I'm going to leave you with this thought. If your system can accurately identify a highly specific face or voice in mere milliseconds using these RAG pipelines, what complex problem will you solve next? The possibilities are truly endless. Thank you so much for joining me on this explainer, and keep exploring.